Okay, so you know how Galadriel says the world has changed? Well, the world of software is always changing too, right? And one thing that never seems to change is the headache of data loss in deployments.
Oh, yeah.
So we're diving deep into reliable message consumption. Specifically, how to make it actually work in the real world of event-driven microservices. And by the end of this, you'll be able to explain it and actually write the code to back it up. We're getting into API snippets, architectural patterns, real-world examples, all focused on how things really work under the hood.
Yeah, the thing is, people often get hung up on just sending messages, right? But the real challenge, that's handling all the things that can go wrong along the way.
Yeah,
In a perfect world, data would just flow smoothly between our services.
really.
But distributed systems, they're anything but perfect.
Right.
You have components failing, connections dropping. It's like a digital obstacle course for your data.
So instead of hoping for the best, we have to design our systems to expect the worst. But before we jump into solutions, let's break down the problem itself. So you have your producer sending events, your consumer acknowledging them, and then poof, data just disappears. Why does this even happen?
Well, think about a typical publish-subscribe setup.
Yeah.
So the producer sends a message to the broker acknowledges, the consumer receives it, sends back its own acknowledgement. Simple enough, right?
Right.
But the problem is that each of those steps, each one, is a potential point of failure. The broker could be down, the connection could drop, the consumer might crash before acknowledging. It's a minefield of issues, even before we get to things like duplicate messages or messages arriving out of order.
Okay, so relying on hope isn't really a strategy. We need something a bit more concrete.
Yeah.
That's where message delivery semantics comes in, right?
Exactly. We're talking about guarantees at most once, at least once, and exactly once. So at most once is like fire and forget, right?
Yeah.
It's cheap and easy, but you might lose messages. Exactly once. That's the ideal, but it's incredibly difficult to do in a distributed system. So in practice, most developers shoot for at least once delivery.
Makes sense better to maybe get a message twice than to risk losing it altogether. But then wouldn't you end up processing the same message over and over? Wouldn't that cause all kinds of problems?
Well, yeah, that is the trade-off. And that's where idempotency comes in. So an idempotent operation, that's one that can be executed multiple times without changing the outcome. Let's say you're updating a user's address. If your message includes the complete new address, then processing it twice won't cause any harm. The address just gets updated to the same value, ensuring consistency.
So it's not just about retrying the delivery. It's about designing your logic to be able to handle those duplicates gracefully. So instead of append this to the address field, you send the whole new address every time.
That's the key. Now, idempotent design is a bigger topic, and choosing the right approach, that depends on your use case. But there are some powerful patterns like ACID 2.0 that can really help. ACID 2.0 focuses on properties like associativity, commutativity, idempotency, and distribution. It's like a framework for building event-driven systems that are actually resilient.
Wait, ACID 2.0, I haven't heard that before. Could you unpack that a bit? I think that'd be really helpful for our listeners.
Sure. So one of the core principles of ACID 2.0 is idempotency. Imagine a stock management system, right? Instead of sending an add 5 to stock message, you could send a set stock to 15 message. That way, even if the message gets processed multiple times, the final stock level is always going to be consistent.
So it's like we're choosing the right verbs for our messages. We're defining the end state we want instead of focusing on incremental changes. But how do we handle more complicated scenarios? What if the message isn't just setting a value, but like a sequence of operations?
Right. Yeah, that's where it gets tricky. We might need to implement deduplication strategies, using unique message IDs, or carefully design our events to be idempotent by nature. It all comes down to understanding the potential failure modes and choosing the right tools and techniques.
Okay, so idempotency helps with the duplicate message problem,
Hmm.
but we're still vulnerable to leaks, right? It's like having a bucket with a hole in it.
You're exactly right. Message leaks happen when a service acknowledges a message before it's finished processing it. Imagine a consumer receives a message, acknowledges it, and then crashes before it actually does the work. That message is gone, marked as consumed, but never processed.
So the key is to only acknowledge message after it's done. Like, don't mark that email as read until you've actually read it.
Precisely. Now, this is where understanding your message broker's configuration becomes critical. So Kafka, for example, it has this auto-commit feature, which can acknowledge messages automatically. But you can also configure it for manual acknowledgements. That way, you ensure the processing is complete before you acknowledge.
So we need to be really careful about when and how we acknowledge messages.
All right.
Better to be safe than sorry.
Absolutely. But even with careful acknowledgement strategies, we still have to be prepared for when things go wrong with external dependencies. That's when resilience patterns like retries, circuit breakers, and bulkheads come in. They're like the safety nets for your microservices, helping them gracefully handle those moments when things don't go as planned.
Okay, let's break down those resilience patterns. Retries seem straightforward enough. If at first you don't succeed, try again. But I'm guessing there's more to it than that.
There is. Retries are great for dealing with temporary hiccups like network glitches or brief service outages. But uncontrolled retries, they can actually make things worse. Imagine your service keeps retrying a dependency that's completely down. You could end up flooding it with requests and bringing down your own service in the process.
Yeah.
So it's not about blindly retrying, it's about retrying intelligently. Some best practices are setting limits, maximum number of retries, maybe a timeout. Then use exponential backoff. That increases the delay between retries, so you're not hammering that service repeatedly. And then there's jitter. That's introducing some randomness to those retry intervals. That helps avoid a synchronized retry storm, where all your services try to reconnect at the same time. Google, for example, uses these really sophisticated retry strategies. They can achieve a 99.9% latency SLA for some of their services.
Wow.
Yeah.
So retries aren't just a quick fix. They're a carefully planned strategy to deal with transient errors. But what about when retries just won't work? Like when a dependency is totally down for a while?
That's when circuit breakers come in. They act like, circuit breakers in your house, right? There's a power surge. The breaker trips to prevent damage. A circuit breaker in software, it prevents a service from repeatedly calling a failing dependency. So it's about proactively stopping the problem from getting worse. Instead of constantly hitting that down service, the circuit breaker gives you a quick failure. So the calling service can handle the situation gracefully, maybe by falling back to a cached response or showing a friendly error message to the user.
So it's like having a little guardian angel watching over your services. Make sure they don't get totally overloaded. But before we move on to bulkheads, I'd love to hear more about how circuit breakers actually get implemented.
Sure, so let's say you have a consumer that uses a Redis cache, right? You could implement a circuit breaker using a library, like Hystrix or Resiliency 4J. So you'd configure it with thresholds for failure rate and timeouts. If the Redis instance starts having errors or it becomes unresponsive, the circuit breaker trips and stops any further calls to the cache. That gives the Redis instance time to recover, and it prevents cascading failures from affecting other parts of your system.
So we're not just talking about an abstract pattern. There are real tools and libraries we can use to make circuit breakers happen in our code. That's great to know. Now, what about bulkheads? You mentioned ships earlier, so I'm curious.
Right, so think about how ships are designed with compartments that are separated by bulkheads, right? If one compartment gets flooded, the bulkheads stop the water from spreading and sinking the whole ship. In microservices, bulkheads do the same thing. They isolate failures so they can't cascade through the system. Imagine two services, A and B, both using the same database cluster. Service B starts doing some resource-intensive work, and it puts a huge strain on the database. Without bulkheads, Service A could get impacted, even though it's not the one causing the problem.
So even though Service A is not doing anything wrong, it could get dragged down by Service B.
Yeah.
Doesn't seem very fair.
Yeah, not at all. That's where bulkheads come in. By partitioning resources, things like database connections or thread pools, we can make sure that one service's load doesn't starve the others. It's like giving each service its own little swimming pool within the bigger database ocean.
Love that analogy. So bulkheads are all about containing the damage from failures. They might not stop the failures themselves, but they limit the impact, right? So the system as a whole is more resilient.
Exactly. Let me give you a concrete example. Imagine you've got a thread pool dedicated to handling requests for one particular service, right? If that service suddenly gets a huge spike in traffic, you wouldn't want all the threads in that pool getting used up by just that one service, right? Because that could starve the other services that also need that pool.
Right.
By using bulkheads, you can partition the thread pool, so you're allocating a specific number of threads to each service. That way, even if one service gets a surge in traffic, the other services can still function normally.
So you're basically creating a safety net for your services.
Yeah.
Making sure they have the resources they need, even when things get crazy. But managing all this seems like it could get really complex, especially as your system grows and you have more and more services interacting. How do you keep track of everything and make sure it's all working right?
That's a great question, and it leads us to the concept of observability. We need to be able to see what's happening within our system, understand how different pieces are working together, and pinpoint the root cause of issues when they pop up. And that's where tools like distributed tracing and monitoring come in. But before we jump into those, let's take a step back and talk about managing persistent state in an event-driven system.
That sounds like a great place to pick up in part 2 of our deep dive. We've covered a lot already, and we're just getting started. We'll be right back after a quick break.
Yeah, sounds good. So, before the break, we were talking about managing that persistent state in an event-driven system. So, you have your service, it needs to update the database and publish an event to, reflect that change. Seems simple enough, but what happens if one of those operations fails?
Yeah, it seems like you could end up with the database showing one thing and the event stream showing something completely different,
Yeah.
which would be a big mess to try and debug.
Exactly. And that inconsistency, it's like a developer's worst nightmare. One way to handle it is to use transactions. Wrap both the database update and the event publishing in one transaction, so either both succeed or both fail. But that works best when everything's happening in the same system. When you have a separate database and message broker, things get a bit more complicated.
Yeah, because the database transaction might work fine, but the message could fail to publish, maybe because of a network problem or an issue with the broker, so you're stuck with that inconsistent state again.
You got it. Now, some developers use compensating actions to try to deal with this. So if that event publishing fails, you basically undo the database update, like hitting Ctrl plus Z to reverse the changes. But even compensating actions have their own issues. What if the compensating action itself fails?
It feels like we're just going deeper into potential problems. Is there a better way to handle this?
There is. It's a pattern called the outbox pattern. So imagine your service needs to update the database and publish an event. Instead of publishing directly to the broker, it writes the event to a special outbox table in the database first, kind of a holding area for events before they get sent out.
So like a staging area where events wait to be dispatched. Why add that extra step, though?
Well, the cool thing is that outbox table, it's part of database. We can use database transactions to make sure that both the state update and the outbox entry are committed together atomically.
Sure.
Either both succeed or both fail, no more inconsistency. Then a separate process picks up events from the outbox and publishes them to the broker, but asynchronously.
Oh, I see. So even if the service crashes after it updates the database, but before the event is published, the event isn't lost. It's sitting there in the outbox, waiting. That's a really clever solution. But what if the database doesn't support transactions across multiple tables?
Great question. In those cases, we can use idempotent database operations. We make sure that if an operation is executed multiple times, it has the same effect. So even if the service crashes and restarts and some operations are retried, we don't end up with duplicate data or an inconsistent state.
So the outbox pattern plus idempotent operations can help us have reliable event publishing, even when the database environment isn't ideal, like a backup plan for your backup plan.
Exactly. And that brings us to a bigger question. What if we treat the event stream itself as the source of truth? So instead of updating the database directly, the service publishes an event, and then both the database and any other services that need to know, they all update their state based on that event.
That's a big shift in thinking, prioritizing the event stream over the database as the real record of what happened. What are the implications of that?
Well, it fits in really well with event sourcing and CQRS, where you're focused on capturing the history of changes, not just the current state. It's like having a log of every transaction, not just a snapshot of the current balance.
That makes a lot of sense for auditing and understanding how things changed over time. But wouldn't it be harder to query for the current state? Like if you need to show that information to a user.
That's a valid point. With event sourcing, querying for the current state usually means replaying all the relevant events, and that can be computationally expensive. That's where CQRS comes in, command query responsibility, segregation. You basically have separate models for updating the system, those are commands, and querying the system, those are queries.
So you might have a separate database that's optimized for handling queries, while the event stream is still the source of truth for all the changes. Like having a dedicated lane for fast queries, separate from the detailed record of events.
Exactly. Now, there's some debate about using message brokers like Kafka as the event sourcing store, because there could be issues with eventual consistency. That means the state across different parts of your system might not always be in sync immediately.
That could be a problem if you need to make decisions based on the absolute latest state, Are there ways to work around that?
There are strategies, like using snapshots to capture the state at specific points in time, but deciding whether to use Kafka for event sourcing is a complex decision. It really depends on your needs and how much eventual consistency you can tolerate.
Sounds like there's no perfect solution for managing state in these systems. It's about understanding the different approaches and choosing what fits your needs and your risk tolerance.
You got it. Now, we've been talking a lot about handling failures gracefully, but what if we could actually use failures to our advantage? To learn and grow from them.
That's an interesting idea. Instead of being afraid of failures, we should see them as chances to make our systems stronger. Like that saying, what doesn't kill you?
Makes you stronger. Exactly. And in software, that's where chaos engineering comes in. It's about intentionally injecting failures into your system to test its resilience.
Wait, so you're saying we should break things on purpose? That sounds a little chaotic.
I know it sounds counterintuitive, but by simulating real-world failures, but in a controlled environment, we can find weaknesses that we might not have even thought of.
So it's like running fire drills for your software, making sure everyone knows what to do when the alarm goes off.
Perfect analogy. Chaos engineering helps us find those single points of failure, hidden dependencies, and brittle assumptions that we often miss. Instead of waiting for a real outage, we create those scenarios to see how our systems respond.
That sounds like a great way to build confidence in your system's ability to handle the unexpected. But how do you actually do chaos engineering? What does an experiment look like?
There are different ways to do it. You could simulate a network partition, a sudden spike in traffic, or even a critical dependency failing. You could use a tool like Chaos Monkey, which randomly terminates virtual machines in your cloud environment, forcing your system to adapt.
So you're introducing controlled chaos to see how the system reacts. But that seems like something that could easily backfire if you're not careful. What are some best practices?
First, start small. Don't try to break everything at once. Begin with simple experiments on a small part of your system, and then gradually increase the complexity as you get more comfortable.
Like a small fire drill before you do a full evacuation of the building.
Exactly. Second, you need a clear hypothesis. What are you trying to test? What outcome are you expecting? If you don't have a clear goal, your chaos experiments won't be very effective.
So it's not just random breaking, it's about having a purpose.
Absolutely. And third, have a rollback plan. What if something goes wrong? How are you going to get your system back to a stable state? Having a good rollback plan helps minimize the impact of any unexpected consequences.
It sounds like chaos engineering is as much about planning as it is about actually injecting failures. But wouldn't all this experimentation slow down development?
That's a common worry. But when it's done right, chaos engineering can actually help you deliver software faster and with better quality. By finding and fixing weaknesses early, you can prevent costly production outages and spend less time firefighting.
So it's an investment in the long-term health of your system. But wouldn't this be more important for large organizations with really complex systems? Can smaller teams or solo developers benefit from chaos engineering too?
Definitely. While chaos engineering is often used with large systems, the principles apply at any scale. Even if you're working on a small project, that mindset of proactively testing failures can be really valuable.
It's about embracing failure as a learning opportunity, no matter how big your team is or how complex your project is. But with all this focus on technical solutions, it's easy to forget about the people. How does team culture affect building resilient systems?
That's a great point. You can have the best technical practices in place, but if your team doesn't have good communication, shared responsibility, and a willingness to learn from mistakes, you're going to have problems.
So it's not just the code, it's the people writing it and how they work together.
Exactly. To build a resilient system, you need a resilient team. That means creating an environment where people feel safe to point out problems, where they're encouraged to experiment and learn, and where they feel ownership over the system's success.
It sounds like building a culture of continuous improvement, where failures aren't seen as personal faults, but as chances to learn and grow.
Right. And that culture needs to be everywhere in the organization, from developers to managers. It's about everyone understanding that reliability is their responsibility.
This deep dive has been really insightful. We've covered a lot, from message delivery to resilience, chaos engineering, and now team culture. It's clear that building reliable systems isn't just about implementing specific solutions. It's about having a mindset of continuous learning and adaptation.
Absolutely. And as we wrap up this part, I want to emphasize that this journey never really ends. Technology changes, systems grow, and new challenges come up all the time. The key is to stay curious, embrace the unknown, and never stop looking for ways to make our systems more robust and resilient.
Great point. And to our listeners, thank you for joining us on this deep dive. We hope you found it valuable and informative. If you have any questions or thoughts or experiences you'd like to share, please reach out. Let's keep this conversation going and learn from each other as we all try to navigate this ever-changing world of software development.
So we've talked about a lot of strategies for making individual services resilient. But what about the whole system? When you have all these services, dozens or maybe even hundreds, all talking to each other, how do you make sure that if one fails, it doesn't cause a chain reaction and take everything down with it?
That's where we need to shift our thinking from individual components to the overall flow of data, right? We need to understand how failures can spread through the entire system. And that's where distributed tracing becomes super important.
Distributed tracing. It sounds like we're about to become detectives, following clues across our entire system. Exactly. It's like giving every request a unique ID, a passport that lets us track it through every service it touches. We can see where it goes, how long it spends in each service, and most importantly, where any bottlenecks or failures happen.
So it's not just knowing that a request failed, it's understanding the whole story of how it got there. Like having a map of the whole city, not just a single street corner.
Precisely. And that level of visibility is crucial for building truly resilient systems. With distributed tracing, we can find the root cause of problems faster, optimize performance bottlenecks, and even spot weaknesses in the system that we might not have noticed otherwise.
It sounds incredibly powerful, but I imagine setting it up can be pretty complex, especially with a lot of services involved.
It definitely takes some planning and work. You need to instrument your code to pass those trace IDs along, set up a tracing backend to collect and store the data, and then use a visualization tool to make sense of it all.
So it's not a simple thing to do, but the benefits sound worth it, especially for larger systems where understanding how everything interacts is so important.
Mhm.
But distributed tracing is just one part of the picture, right? We also need to make sure our individual services are healthy and running smoothly.
Absolutely. Monitoring is key for catching problems early on and understanding the overall health of your system. We're talking about collecting metrics like request latency, error rates, CPU usage, all those key performance indicators that give us a real-time view of what's going on.
It's like having a dashboard for your system with all the vital signs on display. But with all this data coming in from tracing, monitoring, and logs, it can feel a bit overwhelming. How do you make sense of it all and figure out what's actually important?
That's where observability comes in. It's about having the tools and processes that let you ask meaningful questions about your system, even if you don't know exactly what those questions are yet. It's about connecting the dots between all those different data sources, finding patterns, and ultimately understanding how your system behaves as a whole.
So it's not just about collecting data. It's about using it to gain insights, understanding the why behind the what, having a holistic view of your system, and being able to solve problems effectively.
Exactly. And as our systems become more complex and distributed, observability becomes even more critical. It's not enough to just monitor each piece in isolation anymore. We need to understand how they all work together, how failures spread, and how to optimize the whole thing.
This deep dive has been so insightful. We've gone from the very basics of message delivery all the way to resilience, chaos engineering, and now observability. It's clear that building reliable systems isn't just about using certain technologies. It's about having a mindset of constant learning, improvement, and adaptation.
I couldn't agree more. And as we wrap up, I want to leave everyone with this thought. Embrace failures, learn from them, and use them to build systems that aren't just reliable, but anti-fragile. Systems that actually get stronger because of the challenges they face.
That's a great message. And on that note, to our listeners, thank you for joining us on this deep dive into reliable message consumption. We hope you found it helpful and learned some new things. If you have any questions or thoughts or experiences you'd like to share, please don't hesitate to reach out. Let's keep the conversation going and learn from each other as we all navigate the ever-changing world of software development.